first, let's investigate the case of large and positive y. The first step is to look at our exponent function. And investigate if it has saddles. So let's perform the differentiation. And here we go. Indeed, there is a saddle. At point 2y, at large positive values of y, it's to the right and positioned on the real axis in our complex plane. Let's figure out the steepest descent direction. So the second derivative is -1/2. Its argument is pi. And the steepest descent direction as a result is pi n. So it's the horizontal direction along the real axis. So now the question is, can we deform the contour in such a way that it passes through the saddle? Well, of course we can, because we can elongate it. And as we move from the left to the right, we can pass it along this alpha equals 0 direction. But then we have to return also, and we pass the same saddle from the right to the left along the alpha equals pi direction. And both contributions cancel each other. So as a result, the saddle doesn't contribute to the value of our integral, to the asymptotic of our integral. So what would be the next candidate for their important contribution? Well, as you know, it's the branch cut. And indeed, seeing these large values of y, all their all their right part of the contour doesn't contribute to the integral, because it will simply also it will always cancel each other on its way back. Then we have to consider the part of the contour which is not cancelled, and this is precisely the part which circumvents this branch cut. So in the vicinity of the branch point, the behavior of our exponent function is greatly simplified, because as usual we can drop this quadratic term. It's small with respect to the linear one. So now our exponent function is simply the linear function, and for small t. And the steepest descent direction is, of course, the negative direction in the complex plane of t, right? Because we simply have this exponential. So now the integral is very easy to compute, because this contour is simply a Hankel type contour, and the integrand is very familiar to us. It's precisely the integrand that yields gamma function representation, so-called Hankel gamma function representation. And indeed, we just change the variable. So the contour is rescaled into a similar one in the complex plane of S. And once you perform the rescaling, let's call this contour C1 prime. Of course, it will be basically the same contour. And it will be just e to s ds over s to nu plus 1 multiplied by y to nu. And this is nothing but the Hankel representation of the gamma function. And the integral, as you remember, is given by 2 pi I divided by gamma function of nu plus 1 and multiplied by y to nu. So this is the asymptotics of our phi function at large and positive values of y. It blows up at large values of y, but it's okay, because the real wave function is multiplied by this exponential, and for large positive values of y, this exponential will suppress this growth, and so the behavior of the wave function is okay. Now let's figure out the asymptotics of phi function at large and negative values of y. So y is large, but negative. Again, our f function will have a saddle, at the same point, namely at point 2y, but now the saddle is positioned right inside our branch cut. As you remember, the second derivative, the one which defines the steepest descent direction, is independent of the sign of y. So it's again, the argument is pi, and the steepest descent direction is a horizontal direction. So now we actually pass the saddle twice. Once when we glide along the lower bank of our branch cut, and the second time is when we glide along the upper bank of our branch cut. But since both contributions are separated by the branch cut, they won't cancel each other this time. So now we need to compute this contribution. Before we do so, we need to figure out what are the values of our g, multivalued g function, which is here. So let's write it like this. And we define it by the condition that at positive values of t, the function itself is positive. So it's a standard high school definition of their power function. Right, so as we glide along the lower bank of the branch cut, the argument of t is changed by minus pi, negative direction, clockwise, and g of 2y, the value of this function at the saddle, is simply 1 over modulus of 2y times nu plus 1, or 2 nu plus 1, multiplied to e to minus I pi in the same power. So it's in the denominator, or in numerator it will be just e to I pi times nu plus 1. And similar for the upper bank. But the change of the argument is going to be not minus pi, I pi, but I pi. Sorry, just pi. So the sign here will change. And now the contribution itself. Keep in mind that, as usual, we didn't factor out this large factor in our exponent function. So there is no. So when we employ the saddle point formula, as you remember, it's square root of 2 pi divided by the large parameter. Here there will be no large parameter because it's not factored out here. So it's simply square root of 2 pi divided by the modulus of f prime prime times e to f and times g of 2y. So let's compute it for lower and upper bank. For the lower bank, it's passed from the left to the right, and the contribution is, so f prime prime is minus 1/2, so it becomes square root of 4 pi times e to, okay, let's compute the value of our exponent at t equals 2y. So it's 2y squared minus, so it's y squared. Oh, and divided by this, divided by the modulus of 2y times nu plus 1 minus I pi times nu plus 1. Like this. It's for the lower bank. And similar for the upper bank, but it's passed in the opposite direction from plus infinity to minus infinity, and so there will be additional minus sign here. And the total contribution is the sum of these two. And already you probably see that both contributions are proportional to e to y squared. So when we sum them up, they will exceed the contribution from the vicinity of the branch point, because it was just proportional to y to nu plus 1. So it was a power contribution. Now it's the exponential behavior. So the total contribution from the saddle is square root of 4 pi. And when we sum them up, we'll get the difference of the two terms. So it's simply, it's a sine term. So we'll get minus 2i multiplied by sine of pi nu plus 1. And now we clearly have a problem because it blows up too strongly. Even this exponential factor in front of this phi function, which defines our initial wave function, can't cancel this leading exponential behavior. So our wave function behaves like e to y squared over 2, and it blows up. So somehow this solution doesn't fit our purpose. And the question is, if we chose another one, the solution defined by the second contour, could we actually avoid that kind of catastrophe? And the question is no, we couldn't, because this contour, it's already bad from the start, because when we compute the integral along this contour for large and positive values of y, then this saddle is passed only once from the left to the right. So even this contribution won't cancel. And that means that for large positive values of y, this behavior would be just a similar exponential type behavior, and the wave function will blow up. So both of these contours doesn't suit our purpose. They don't lead to bounded solution at large positive or negative values of y. The question is, what are we going to do now? So how can we actually build the bounded solution? And the answer is we need to impose additional condition on the coefficients of our initial equation. For example, look here. This contribution will vanish if this new parameter is integer. And here it hints to the correct restriction on our initial parameters of our differential equation. For example, if nu is integer, then the whole analytical structure of our solution changes in the complex plane, because there won't be any need for a branch card. All right, so and now finally we know what to do. We impose additional conditions. So for the solution to be bounded, we have to impose this condition nu seems to be we seem to need to put nu equal to some kind of integer.